So we had done making disubstituted benzenes. So let's just remind ourselves about this stuff real quick. All right, so two things you have to do. Remember what you're adding, and then figure out where it's being added based on what you have on the ring. So what does SO3H2SO4 add? SO3H. And then does the methoxy group direct ortho para or does it direct meta? Ortho para. So we're going to end up with two possible products. Okay, we're going to end up with the one where the group is added ortho and the one where it's added para. So for the next one, BR2 FeBr3 adds bromine. And then the ester is at ortho para or meta directing? Meta. So we're going to add a bromine. And we're going to put it meta to the ester. And then the last one, what are we going to add? I. And then where's it going to go? Orthopara or meta? So this one, my handwriting's awful. It's an NO2. All right, so NO2 directs meta, and H2 directs orthopara most of the time. So just don't get those confused. NO2, meta, and H2 most of the time orthopara. Easy enough? All right, so now we're going to talk about what happens when you want to add a third or a fourth group to your ring. How do we do that? Right? How do we determine where that third group or that fourth group is going to go? Right? So there are two factors that you need to consider. The first is electronics. And this is just where all the groups that are already on the ring, where are they directing? Where are all the groups that are there? What carbons are they activating for the electrophile to add to? Right? And the second thing you have to worry about is sterics. And this is just how easy a position is to reach for the electrophile. Okay, so how easy is it to reach that position? Right. Our general rule here is is you don't add between two groups. So you don't want to kind of squeeze in and end up with three groups in a row, right? And we'll show some examples of that here in a sec. And then the other thing is that tert-butyl blocks its ortho positions. So if you have a tert-butyl group on a ring, you can't add ortho to that tert-butyl group. The substituent is just too big, and the electrophile won't be able to get to those positions with the tert-butyl group there. So I'll just show an example of that because it's pretty easy. So you've got your tert-butyl benzene, let's say. We want to add isopropyl. Right, tert-butyl directs ortho-para. But because tert-butyl is so big, we can't add to the ortho positions. So we'll only get one product here. We'll only get the para product because the tert-butyl group is too big. This isn't something that is just limited to tert-butyl. Basically, the thing that matters, like tert-butyl is the easiest one to see, is that this carbon right here, right, I'll make it blue, that one. So this carbon right here, it's quaternary, right? It's bonded to 4 other carbons. That just means that that carbon ends up with a lot of carbons coming off it, ends up being big. So if it's not tert-butyl, if it's some other quaternary group or quaternary carbon, right, that's still going to do the same thing, right? That carbon, this carbon right here, the one that's bonded right to the ring, is quaternary. So that is still a big group that is going to block its ortho positions. So we're only going to end up with the para product. So just having any quaternary carbon on your ring is pretty much going to block its ortho positions. So the other part of sterics will work in as we do the electronic stuff. All right, so our substituents can work together, meaning that all the substituents are kind of pointing to the same carbon for the electrophile to add to, or they can work against each other. They can point at different positions to add the electrophile, right? So they can either all be working together to say, hey, this carbon right here, electrophile add, or they can be working against each other and activate 3 or 4 positions, and then the electrophile is like, I don't have a clear direction. Right? The easiest one is when the groups direct to the same position. That's the easy one, right? So that is something like, say we have something like this, and we add this. So what I like to do is I like to kind of color code the substituents and kind of show on the ring where they're directing. So let's say I'm going to use a green dot for the methoxy, right? Where does the methoxy group direct? Ortho-para or meta? Ortho-para. So it's going to direct here and here, and there's already a group on the para position, so I can't put another group there. So even though the methoxy group can direct para, once there's already a group at a carbon, you can't add a second group. So it's going to activate the two ortho positions. And then sulfonic acid, SO3H, does it direct ortho para or does it direct meta? Meta, very good. It directs meta. So it's going to direct here and here. So these two groups are working together and they're activating the same two positions to get the electrophile, right? So we know that we're going to just put our nitro group on one of those two carbons. Here it's symmetrical, so it doesn't matter which side you put them on, right? They're just going to work together. I'm going to do the same thing. We're going to say, all right, I'm going to go here and here, right? My nitrogen directs orthopara. My methyl group also directs orthopara. So here they're activating the same positions, right? Now, kind of like when we had direction to orthopara before, you just got to get a mixture of products, but we can eliminate one of the positions. So we can eliminate this position due to sterics. Right? So don't add your electrophile between two groups if you can avoid it, right? So here, I can just eliminate the position between the nitrogen and the methyl because I have other perfectly good, perfectly activated positions to go react with. So that electrophile is not going to want to squeeze itself between two substituents when it has another carbon that it can get to without having to do that. So I'm going to end up with two possible products. Plus, and this is just like when we had orthopara stuff where you're going to get a mixture. Like if I give you one of these two products as an answer, you could just pick that. That would be fine because it's going to be hard to predict which one's major, which one's minor. So I think about the like not adding between two groups as like, remember when you could go to bars and hang out with people? This was a time, right? And like maybe there were like 5 of you, and one person was like, I'm the DD, I got you. Everyone pile into my car. And there were 5 of you, so one of you had to sit in the middle seat, and you were just like, oh, this is awful, right? I'll call an Uber instead. I'll do anything but sit in the middle seat. That's what the electrophile is like. It's like, I don't want to get squished between these two substituents. I'll go do something else. I'll go somewhere else. Please don't make me go in between these two groups, right? Like you're like, put me in the trunk. I'd rather be in the trunk than in the middle seat, right? Now, story time. We've all put someone in the trunk at some point in our lives, right? It's just a thing that has happened. I drove a station wagon in grad school. I was that cool. And so we were going to a Pizza Hut all you can eat buffet. Classy. Peak culinary, right? And so we all pile into the station wagon, and one guy ends up in the back of the station wagon, of course. And so we're driving. We get to the Pizza Hut, and the little cargo cover was pulled over him. I was like, well, that's weird. And when I open it up, he rolls out, and he has his hands and feet duct taped with duct tape over his mouth, and he rolls it on the ground like I had kidnapped him. And I was like, so he just found some duct tape in the back of my car, taped himself up, and then rolled out and made it look like in the middle of noon, lunchtime, just rolled out in a parking lot. I was like, like I kidnapped him. I was like, Oh no, please, please, I didn't take him. He did this to himself, right? But your electrophile is like, I would rather go in the back of the station wagon and tape myself up than go between these two groups, right? So you're looking for the place that is most activated, basically that has the most dots, and that is then easy to get to. Sorry. Oh, that works. People are yelling at me right now. I can just feel it. All right. So here, we're going to go through and do the same thing. We're going to kind of assign everyone a color and then figure out where they're activating. So this nitrogen directs ortho para. One ortho position is blocked, one para position is blocked, so it's only activating there. Methoxy directs ortho para, so here and here. Nitrogen blocks its other, its para position. And then we'll methyl group. Methyl groups direct ortho para. Right, so we're going to go to the position that has the most groups pointing, hey, go here, right? So the methyl and the methoxy are both saying add to this carbon or this carbon. This one's between two groups, so we can eliminate it. So we're just going to add our group there. Next one, same kind of thing. Nitro group's going to direct here. Methyl group's going to direct here and here. Nitrogen's going to direct here and here. Right, so we're going to go to the one that has all three groups directing towards it. That's the one we're going to prefer to go to. I'm going to point out real quick that amides are not impacted by strong acid. So if that was an NH2 or two like methyl groups, right, then it would go from being an activating group to being a deactivating group. But putting the C double bond O on it makes it so that nitrogen is less basic, so it always stays an activating group. So it doesn't, those don't switch. Only the NH2s or two methyls or two ethyls or whatever switch. They get protonated. But when they're an amide, they don't get protonated. Seem reasonable? So basically, you're just trying to find the position that has the most dots, right? That you get a clear sense of like, this is the most activated carbon for me to add an electrophile to. This is the most negative carbon in the molecule. That's where I'm going to go. And if there's a tie, you're going to go like, okay, which one of these two is easier for me to get to? I guess I forgot. Nitro would have directed there as well. I don't know why I forgot that. Oh, I know why. Baby only let me get 6 hours of sleep. Baby! And then the cat woke me up vomiting. Cat! All right. Now, what if your groups direct to different positions? So you end up with no clear carbon to add to, right? There's not a clear winner when you're doing this. The general rule is the most activating group wins. So this is where like kind of having a sense of the order of which groups are more activating is important, right? Knowing that it's O minus, then nitrogen, then ethers and phenol, and then like nitrogens on amides and then alkyl groups, knowing that general order will be useful because you go like whichever one's more activating, that is the one that I'm going to kind of like let steer the ship, let determine where the electrophile is going to go. So if you have, say, right, your nitrogen wants to direct ortho-para. It wants to direct here and here. Your methyl group wants to direct ortho-para. It wants to direct here and here. So they're just basically saying, hey, all these carbons are positive, right? The group that is most activating is the one that's going to kind of win, right? Because it's making a carbon more negative than the other group. So nitrogen is more activating than an alkyl group. So it's making the red dot carbons more negative, which means the electrophile is more likely to add to it. So we're going to add our group here, right? And that is going to be our product. So a lot of times when you have multiple electron donating groups on your ring, you're going to add more than one electrophile. You're just going to keep adding electrophiles. We're always going to stop at one in like class, just because it's a lot for you guys to keep straight. Like, oh, this has more than one activating group. Maybe I should add two things, or do I just add one? So we're just going to stick with you add one. But in lab, if you look at the reaction that we did in lab, or we're going to do in lab, right? So this is just the water and the acid. That's just a way to make a carbocation. We end up adding two of them. Right? Because your methoxy group activates here and here. The blue one activates here and here. And so you add one and then you add another one. But for us, we're just going to stop at one, just to make it a little bit easier. That make sense? So what if I have yeah. All right, so let's see where everything's directing. Our methyl group is directing ortho para to itself. The nitro group is directing meta, which leaves only this position, right? Because it's the methyl group's at its other meta position. And so we have all of them are just activated by one group, right? So how do we pick? Well, we can eliminate the group between the two substituents, not going to squeeze in there. And then we can eliminate the group that's being directed to by the deactivating group, right? The deactivating group isn't doing a whole lot to encourage the group to add there. It's just that's the least bad choice. The activating group is actually making the positions that it directs to better places for the electrophile to go. So we're going to add to one of the two blue dots. So we're going to end up with the group being ortho. What's this space here? It's going to be ortho to the methyl group. Oh my gosh. Plus, you're going to get somewhere it is para to the methyl group.
So the question that I got was, do we have to draw both on an exam or only one?
So if I was going to have you draw, what I normally do is I just say, like, pick one. As long as it's one of the two correct ones, I am fine. Since your test is going to be more multiple choice, as long as it's like, I'm not going to put both of these as like two different options. It'll be like one of them. As long as it's one of the two products you could get, that would be the one you would pick. Right. So here, the methoxy directs ortho para. The nitrogen, so this one's tricky, right? This has got the nitrogen and then a strong acid, right? So our nitrogen is going to go from being activating to being deactivating, right? Because it's going to react as the positively charged nitrogen. So it's going to direct meta to itself. So we end up with the exact same situation. It's just you had to recognize that the nitrogen switched from being activating to deactivating because there was strong acid. So again, we're going to get the same kind of similar products we had before. So I'll point this out now. Some people get confused by I flipped my NO2 or I flipped my SO3H, right? So like here, right, it was SO3H, and up here, right, it's kind of backwards. The reason I do that is the way when you write these abbreviations, you're conveying bonding, right? So I'm trying to show that this sulfur is bonded to that carbon. Right, if I wrote it SO3H, if I wrote it like this, SO3H, it would look like I was saying the hydrogen was bonded to the carbon of the ring as opposed to the sulfur. So that's why I turn it around so I can have the carbon bonded to the sulfur. Same thing like, here, right, I have NO2 this way, then I switch it around so I can show that the nitrogen is bonded to the carbon. So it's just a way to make sure that you're always showing that you have the right bond connectivity, right? That you don't have you're not saying, hey, the oxygen and the carbon are bonded together, and NO2 is like, well, no, the nitrogen's bonded to the carbon. So that's why I switch it back and forth, depending on like what side of the molecule I'm drawing it on. And then here, let's go blue dot, activate here, here. Green dot is going to activate here and there. What's more activating? A methyl or a methoxy? Methoxy is. So methoxy gets to choose where the electrophile goes, right? It's making the green dots more negative than the methyl is making the blue dots. So the bromine is going to go where the methoxy is directing. So far, so good? So our tert-butyl group is going to direct ortho-para to itself. Our methoxy is going to direct ortho-para to itself. But tert-butyl is big and blocks its ortho position, so here and here get eliminated, right? You can't add beside a tert-butyl group easily, so that just leaves one position that we can put our ketone. So we should only get one product. Here, this methyl is going to direct ortho-para to itself. This methyl is going to direct ortho-para to itself. Nitrogen is going to direct ortho-para to itself. We only have 2 carbons that are activated twice, and one of them is between 2 groups. So again, we're only going to get one product. So it doesn't really matter how many groups I've kind of put on your ring. And like what they do, you can just go through and kind of work through it the same way. If I had 4 or 5 groups, well, 5 groups, you know exactly where it's going to go, right? But you can just work through where everything's being directed and just find the position that's being directed to the most, and that's where you're going to put your group. So there's kind of another version of this where you have 2 strongly deactivating groups. On the ring. So you have like a nitro and like a nitrile. We're going to get no reaction here. Bless you. So the ring is too electron poor to react. So we're going to kind of make like a rule of if you have just two electron withdrawing groups on your ring, we're going to say it's not really going to react. Right? Because both of these groups are pulling electrons out of your ring, which means your electron doesn't have enough electrons to go add to something else, right? It's short electrons. The last thing it wants to do is go give electrons to something else. If we add an electron donating group, we turn the ring back on. Right, so we can take the same molecule, but add an electron donating group. Say, right, so this is gonna just put enough electron density back in the ring that the ring's gonna be able to react again. So then we can go through and do all of our normal stuff. This goes here. This goes here. This goes here. So we're going to add our group ortho to our aniline. Seem reasonable? So two strong electron withdrawing groups, nothing, no reaction. But if you start putting electron donating groups back onto the ring will start doing additions again. Cool, cool. So that should be all of electrophilic aromatic substitution. You've got your like 7 reactions that you need to remember. And then you've got kind of all of your rules for where the groups are going to be added to the ring as you add more groups. So like the first group's easy, then okay, second group, where does it go? Third group, where does it go? So you kind of have all those rules down. So we're going to do some more reactions, some different types of reactions. And the next one we're going to do is the nucleophilic aromatic substitution. What we kind of talked about at the beginning is the kind of the partner to electrophilic aromatic substitution. So here, benzene is electron poor and attacked by a nucleophile. So here, the benzene is the electrophile. Right? It is the E+. It is the thing that needs electrons. For the benzene to be the electrophile, for a benzene to be electron poor enough for these reactions to work, you need to have 2 electron withdrawing groups on the ring. And normally, one is a halide. So you have one of our electron withdrawing groups that we talked about before as being deactivating, plus a halide on the ring. And that will make these reactions work. Ideally, these groups are orthopara to each other. When we go over the mechanism, I can show you why them being orthopara matters. So let's kind of look at a generic example of this reaction. Right? So you're going to have some electron withdrawing group and then a halide. You're going to add a nucleophile. and you're going to end up substituting the nucleophile for the halide. This is not an SN2 reaction, right? Even though like the net transformation looks like an SN2 from last semester, where you're like, oh, I have a halide, I have a nucleophile. The nucleophile took the spot of the halide, right? It's not an SN2 reaction or an SN1 reaction, right? Because you can't do these reactions at sp2 hybridized carbons, right? You can't do them when your halide's on a double bond. You can't do an SN1, you can't do an SN2. So this goes through a different type of mechanism. These are addition elimination mechanisms. Right. So what ends up happening is you have your nucleophile, and it's going to add to the carbon that has the halide on it, and take the electrons from the double bond and push them onto the carbon that has the electron withdrawing group. So you're going to get this negative charge beside the electron withdrawing group. So the electron withdrawing group is helping to stabilize that carbanion, right? It pulls electrons out of the ring. So putting electrons by it, it can help stabilize it. Now, these electrons will come down and push the halide out to generate the product. And the halide. So step one is the addition. Step two is the elimination. So this is similar, the elimination is similar to when we did elimination reactions like E1 and E2 reactions in organic 1, right? Where like you pull off your hydrogen and the electrons in the carbon-hydrogen bond fall down and push off your halide. This is similar, right? I've got this negative charge, it falls down to make a double bond and pushes the halide off in the process. The first step, the addition, is the slow step. It is the rate determining step, right? This makes sense. It kind of mirrors what happens with electrophilic aromatic substitution. I go from being aromatic to being a non-aromatic ion. I go up in energy. Going up in energy takes work and it's hard to do. So it takes a long time. So going from aromatic to non-aromatic is uphill and so is slow. Once I have that, the second step is the fast step, right? So I go from stable to unstable. The second step is going from the unstable non-aromatic ion back to a stable aromatic compound. That happens really fast. Right, so you can think about it as once you do the first step, as soon as you get here, that compound is going to go right back to being aromatic. It's not going to hang out at the ion very long. It's going to be like, oh, electrons come down, spit out this halide, and back to being aromatic. Right? So this first step, right, the addition, is got a funny name, or it's an Ipso Attack. And Ipso just means attacking a carbon on the aromatic ring that already has a substituent. So Ipso just means attacking the carbon that already has a non-hydrogen group on it. This is where I got with the first section. So we're going to stop here. We're going to pick up from the mechanism, and we're going to talk about how we can speed up the first step. Because anything we do to speed up the first step of the reaction speeds up the overall reaction. So I think that's all we have. And put your minds at ease. There's not nearly as much nucleophilic aromatic substitution stuff as there was electrophilic aromatic substitution. In my slides, it is one slide as opposed to 15 slides for electrophilic aromatic substitution. So much easier. So with that, I will see you guys next class.